Hello, welcome to our today's tutorial. I'm David and I hope you will enjoy. So today we want to look at the design of a pad footing using the BS8110 code. The question is design a concrete square footing to support characteristic axial load of 1000 kilonewton dead load and 300 kilonewton imposed load from a 450 millimeter square column using punching shear design. Use the following information. We've been given strength of concrete, strength of steel, self-weight of column and footing, self-bearing capacity of soil, and cover to reinforcement. This is how we shall proceed. First, we shall obtain what has been given. So those are imposed, dead load, dimension of column, etc. But now, step number one, we shall start by calculating the planned area of base. Now, when calculating planned area of base, we use the serviceability limit state, SLS. Remember, in reinforced concrete design under BS 8110, we have two types of limit state. We have the ultimate and serviceability. Now, for the case of planned area of base, we use the serviceability limit state, where the factors for dead and post load is 1.0. It is the same, just 1.0. Now, under planned area, we shall compute dead load. Total dead load here will become the applied total load plus self-weight of footing and column, which is 1000 plus 150, 1150 kilonewton. Imposed load we've been given as 300 kilonewton. Now, as I've told you, serviceability load consideration here, design axial load N will be 1.0 dead plus 1.0 imposed. That is why we have 1 times 1150 plus 1 times 300, giving us 1450 kilonewton. Then planned area of base now will be equivalent to the design axial load based on serviceability load consideration divided by the safe bearing capacity of soil. Here we use it as Q safe. Now that is 1450 divided by 200, which will give us 7.25 square meter. Now, because remember, if the column is a square, automatically the pad footing, the pad will be a square. Now, for us to get the dimension of this particular pad, we will have to square root the plan area of base, which will give us 262.69 meter. Hence, in this case, we can round off or round up, and we opt for a 2.7 meter square base or square footing, which will have a plan area of 7.29 meter squared. Step number 2, we will go to bending reinforcement. Now remember, for bending reinforcement, we use the ultimate limit state, where we use 1.4 factor for dead and 1.6 factor for imposed load. Now, design total ultimate load W will be equivalent to 1.4 dead load. Now, in this case, the dead load, we exclude the self-weight of footing and column. We don't consider it at this particular stage. That is where you find it is 1.4 times 1000. Now we don't include the self-weight. Plus 1.6, QK was 300, we get 1880. Now from there, we compute the earth pressure. Earth pressure PS is normally given by the ultimate load divided by the plan area. Remember, plan area is 7.29. We get 258 kilonewton per square meter. Something to let you know is we normally make an assumption the earth pressure is acting upward, is now pushing the footing upward. Now, ultimate moment of now design moment here, it will have a maximum value at the face of the column. So the maximum value will be at the face of column. Now we are considering it from the end of the footing here. Now, the maximum design moment at the face of the column is given by the earth pressure PS times this distance here, distance from the end of footing to the face of column. How do you compute that distance? It's basically a half times length or side of footing minus a half the length of column or a half size of column. Why? Because look at this. If I measure from here, if I take distance from here to the center of column, that is a half of the footing. But now my interest is at the face of column. So I will subtract a half of column to have that point here. That is why we are ending up with a value of 1.125 as the distance from the edge of footing to the face of column, because it is basically, if you divide 2.7 by 2, the half of length of footing, it will be 1.35. This 1.35 subtract the column measures 450 millimeter, which is 0.45. If you divide it by 2, you find something close to 0.225. Now, when you subtract, you end up with 1.125, but now it is a design moment is earth pressure times that distance squared over 2, which will give us 163.27 kilonewton meter per meter. Something to let you know is that we normally design our footing the same way we design our slab. That is why you see now we are ending up with a value, a moment in kilonewton meter per meter. Then now from there, we move to the ultimate moment of resistance. We know that ultimate moment of resistance is the internal capacity of a concrete member, what it can accommodate. We have seen the applied moment is 163, but now what is the internal capacity of our pad footing? Is 0.156 FCU BD square. Now at this point, you have to assume to make an assumption of the diameter of the bar. Now, I told you to make a competent assumption. Look at this table here, this reinforcement table. The diameter you assume must appear here. You don't just make an assumption, but it must be along among the given diameters. You cannot make an assumption of 25 millimeter diameter. That will be an incompetent assumption. The diameter must be amongst the standard diameter sizes given. I hope that is okay. Now we will proceed. And now here and say we assume bar of diameter 16 millimeter, and then which will be in both direction. Remember, this is a square, so they will run in both directions. They will be perpendicular to each other. Then now we have a curve of 40 millimeter have been given. Now we know that self-weight of footing is equivalent to planned area times overall thickness of footing times the unit weight of concrete. Just like we know for the case of slab, we used to take self-weight is a unit weight times overall depth, but in this particular case, because we want it in terms of kilonewton, we will multiply by the planned area to remove per meter square. So self-weight of footing is planned area times overall depth of footing times unit weight of concrete. Now, which means if I have to make my overall depth of footing as the subject, I will take self-weight of footing over land area multiplied by unit weight of concrete, which is we are given as 150, but remember this 150 was self-weight of footing and column. But now we just use it 150. I divide by plan area of 7.29. Unit weight of concrete, we know it is a 24 kilonewton per square meter. This will give me 0.85 meter. But now remember, I cannot take 0.85 meter as my overall depth of footing. Why? Because remember the 150 kilonewton, there is also the self weight of the column. Now, to be on the safe side and also for practicality, you cannot provide a near 1 meter depth of a footing. It will not make sense or from economic perspective. Now we shall adopt a value of overall depth of the pad footing as 600 millimeter. The condition is that when you are computing the thickness or the overall depth of this footing, you must ensure that the assumed self-weight is not exceeded. Remember, when we take a value of 600 millimeter, the value will be below the 150 kilonewton given. Now, for practicality purposes, we can adopt the 600 millimeter. Now, here, the effective depth D for this particular pad, we use a slightly different formula. Remember, for the case of slab, we take diameter of bar over 2. But for this case here, because we are making it known that we shall have bars running in both directions, we take the overall depth, subtract the cover, subtract the diameter of the bar, which will be 600 minus 40 cover. We said we take diameter 15 millimeter, which will give us 544 millimeter. Now, the ultimate moment of resistance, which means the capacity, what the footing can withstand, is 0.156 times 40 times 10 power 3. Remember, 10 power 3 is B. Footing and slab, we design them the same way. So 1 meter, which is 1000 millimeter or 10 power 3 millimeter, times D times 10 power negative 6 to change from Newton millimeter to kilonewton meter. For this case, you find MU, the moment of resistance is greater than the applied design moment, hence no compression reinforcement is required. Generally speaking, most of the times you find that the slab for which a footing is a special slab, we don't need the compression reinforcement. Most of the time or all the times, the ultimate moment of resistance is more than the design moment. Now from there, we'll go to area of main steel. We know that we have to compute a coefficient K given by M over FCU BD squared, where M is the design moment, we had it, we substitute. Strength of concrete we are given as 40, that's why we have that 40. So we shall get a value of 0.0138. Then you go to lever arm Z. Remember we said the value of Z should not exceed 0.95 effective depth D. So if we substitute compute, you find that our Z here using the value of K, it will be 0.98D, which is not acceptable. In that case, we take Z as 0.95D, which will be 517 millimeter. Now, area of steel is given by design moment divided by 0.95 FYZ. Design moment, we multiply by 10 power 6 to convert it into compatible unit like those in the denominator. So we know that strength of steel was 460. Our Z is 517, and then 0.95 is a coefficient, or we can say it's just a number we use due to based on the version of the BS8110 code. So we get 723 millimeter square per meter. But remember, for Fy is equivalent to 460 Newton per millimeter square, the minimum area should be 0.13% of BH. Now, 0.13% of BH. Remember when they say 0.13%, it means 0.13 over 100 times B, which is 1000 millimeter or 1 meter, times H, which is 600, we get 780 millimeter square per meter. Now, this implies that our AS must be greater or equal to AS mean. Now, since our AS is 723 and our AS mean is 780 millimeter per meter, we disregard our AS and then we go to the table to read the value corresponding to the AS mean. Now, let us go and read. Now, remember we had assumed our diameter is what? 16 millimeter. Now we are looking for a value of 780. This is our table. Now I will move along 16. I will come this way. This is my 16. I move. I'm looking for 780. 780. Now I'm here. So the value close to 780, but of course, which will be equal or greater than that is 804. 804 millimeter square per meter. It means I provide bars of 16 millimeter diameter spaced at 250 millimeter center to center. That is why here we'll come and say provide H16 at 250 center to center as read from the table, because for the case of slab or pad footing, when you read the area, it must be diameter of bars and the point of the diameter of bar and the spacing. So we have to provide H16 at 250 center to center, remember in both directions. Then we have punching shear. For punching shear, first of all, you have to calculate the critical perimeter. The critical perimeter. This is what we call the critical perimeter. This is the critical perimeter. So critical perimeter is given by the perimeter of the column plus 8 times 1.5 D. 1.5 effective depth, but we know that our column is a square and we know the perimeter of a square is 4L. That's why we have 4 times 450 plus 8 is constant times 1.5 is constant times our D is 544. It gives us 8328 millimeter. Then our area within the critical perimeter, we take the length of column plus 3 effective depth, all that squared, which is given by 450 length of column. 3 is a constant, our this 544. We multiply or we square it. Remember, this will be millimeter square, but we know 1000 millimeter is 1 meter, meaning 1 million square millimeter is 1 square meter. That's why we have 10 power negative 6, which will give us 4.33 meter square. Now, the ultimate punching force V is equivalent to load on shaded area. Load on shaded area. Now, load on shaded area. Now, this is the shaded area. I think I can show you. So this remaining thin area is the shaded area. Now we are looking at load on shaded area. This is the shaded area. Will be equivalent to earth pressure into bracket plan area minus area within the perimeter. That's right, because already this unshaded area is here 4.33 and the entire area is plan area. So if we want to determine the shaded area, we just take the total plan area we had, we subtract the area within the critical perimeter. That's why we are saying the ultimate punching force here, it will be earth pressure into plan area minus area within the perimeter, which is 258, remember, kilonewton per square meter. You multiply by 7.29. This is what? This was the plan area, and then 4.33 is the area within the perimeter here. And now from the design punching shear stress, remember we said in structures perspective, pressure is stress. So here, the design punching shear stress will be equivalent to the punching shear force divided by critical perimeter multiplied by the effective depth. Now, our punching shear force, we had it as 763.68 kilonewton. We changed to newton. That's why I'm multiplying by 10 power 3. Then critical perimeter, it is here. We calculated it here as 83.28, and then our D, we had it here as 544. This is our D. Now we get a value of 0.169 Newton per millimeter square. Then we look at shear stress of concrete VC. Shear stress of concrete VC, in simple terms, it means the capacity of shear the concrete can withstand. For this case, we do what? We have to compute a parameter 100 AS over BD. And in the previous lecture, we said that this AS is the area provided. Now remember what you read in the or from the table. It is here, 804. So 100 is a constant, 100 times 804. B, we said this is 1 meter width, which is 1000 millimeter. D is here, you find it is 0.15. Now let us go to the table. If we go to the table, in the table we have 100 AS, and then we have the effective depth. This is the table I'm talking about. This is the table. Now, when we come to this table here, this table has two columns. We have a column for 100 AS over BD, and we have a column for effective depth. Now, the value of our effective depth is 544, meaning it will lie in the column greater or equal to 400 millimeters. So it will lie here. And then we've computed our 100 AS over BD is 0.15, meaning it is this one here, and now at the point of intersection here, this will be the concrete shear stress from the table. That's how I got the 0.34. Now, once I get the 0.34, I will come here. Remember 0.34? These tables were made on assumption, or were made on the criteria of an FCU of 25 Newton per millimeter square. But what we are using is 40 Newton per millimeter square. Now we have to modify it by taking the FCU over 25 power a third multiplied by what we read in the table, which is 40 over 25 power third times 0.34, which is 0.398 Newton per millimeter square. Then we can say, since the shear stress of concrete, the capacity of concrete in regard to shear is more than the shear stress from the applied forces, then punching shear is unlikely. and 600 millimeter depth of slab is acceptable. Remember, all slabs, the amount of shear stress of concrete is normally greater than the ultimate punching shear stress. Now, when we come to reinforcement detailing, this is how it will look like. Now, this first line here, this line here means it refers to these bars which are running upward. So it indicates that it is H16 at 200 center to center, alternate bars reversed, just as I said from the previous lecture. Most of the time you find that alternate bar reversed means if this bar run from the end here, it will stop here. Now the second bar will start from here, we run, but it will not reach the end. This is what we call the alternate bars reversed. So no bar join the two ends, but if a bar starts from this end, it will stop some distance before the other end. Why? Because just like we've said, maximum design moment will occur near the face of the column. So as you near the edge of the pad, you find that the quantity of bending moment is very low, hence you don't need the 100% of steel to reach in that particular area. That's what we mean, alternate bars reverse. So this is our column, and this is what is inside here is our column, and then this is our footing. Now this is what we call reinforcement detailing. So if you take it to a construction site, whoever is implementing will know that the bars should be similar in both directions, and they will be of 16 millimeter diameter, spaced at 250 millimeter center to center. Thank you so much for listening. I hope you've enjoyed. Kindly like, subscribe, and share my YouTube channel. And if you have a comment, feel free to comment so that we can improve our work and make it more impactful. Thank you. See you again.